I hope you can hear me.
Yeah, we can hear you well.
Okay, great. And I'll share the presentation, right?
Yeah. Thank you.
Okay.
So Giorgio has got his master at University of Bologna with Andre Cosmatri, and he got his PhD at the University of La Sapienza in Roma with Fabrizio Fiora. Please correct me if I was wrong.
Fine.
He's always working on AGN X-ray surveys, the search for elusive obscure sources through spectroscopy, variability, multi-wavelength selection techniques. He kept working on these topics during several postdocs in Bologna, at MPE in Munich, and at the Observatory of Athens. More recently, he got also interested in AGN winds outflows, in particular ultra-fast outflows observed in X-rays. In 2014, he came back to Bologna, where he is now, since 2018, a staff researcher at the observatory. So today, Giorgio will talk to us about the Athena science and simulation. So the floor is yours, Giorgio.
Okay, thank you very much. So hi, everyone. Thanks to the organizers for the invitation and a nice presentation. I'm sorry I cannot be there in person. Actually, it's been a while since I visited CFA. I see a few familiar names connected in Zoom. So hi to everybody. Today I'm going to talk about Athena-WFI surveys and simulations that we've been carrying on in the last few years to assess the performances of such survey, and at the end I will put these performances in the broader context of future facilities and surveys. First of all, a disclaimer: as you probably know, this summer ESA took the decision of putting the mission on hold due to budget problems mainly. So now Athena is undergoing a redesign process. So if you're curious, we can discuss more about this process in the question. The bottom line is that if there will be a mission, which is not granted, there will be for sure cuts and reduction of the performances. We expect this to affect mostly XIFU and the mirrors, because these are the most expensive and complex parts of the mission, and not much the WFI. So all the work that I will present, of course, was done before this bad news, let's say, and we'll need an update at some point for sure. But we think, and we have shown in the past, that we can recover most of the original goal of the surveys as far as we can get a PSF size that is close to the original goal of 5 arcseconds. And as you will see, that PSF is really critical and hard to recover. Okay, so let's start. The Athena-WFI survey responded to one of the two main goals of Athena, that was as stated in the Athena science requirement document. Athena shall determine the nature of seeds of the earliest growing black holes and blah blah, basically identifying hundreds of AGN at redshift greater than 6. And you can see here, I hope you can see my pointer. You can see here how these hundreds of AGN at redshift greater than 6 can constrain the luminosity function in the original work by James Head based on his luminosity function. And you can see also a couple of different extrapolation of the luminosity function at lower redshift that gives you already an idea of the broad range of values that are they span. So for practical reasons, this broad goal was translated into two aims, that is detecting at least 10 AGN into the different redshift and luminosity beams. You can see the numbers here. And this is very convenient because this translates directly into two requirements in terms of flux and area that you need to cover to recover this goal, again, based on one luminosity function. And you can see here in this flux area plot an analytic derivation of the sensitivity survey of the sensitivity of the survey and how these met these two goals, again from the original proposal document. Together with other science goals, first groups at high redshift, Compton peak AGN, AGN outflow again at high redshift. This brings the survey to a total of more than 23 megaseconds in the mock observing plan, as it was in the last years. basically one shallow large area survey and one deeper with slightly different pointings, but it's one deep survey. And this is about 1/4 of the mission lifetime expected. So we decided to test all these predictions and these performances with end-to-end simulation to back up our analytic estimates, and also to test the different the impact of different design during the study phase. And in doing so, we use the 6A simulator, which is a multi-mission X-ray simulator, very flexible. Basically, you build your mock catalog of sources that you want to observe, and then you have files describing the telescope and the detector, and you end up with realistic event file that of what that specific telescope would observe, that you can then analyze with your preferred tools. And if you change your telescope design, then you can run the simulation again and getting the different result for that change in the design. And you can see this is the website, and this is the list of instruments that are already supported, and it's a list that is always growing. So we started from the mocks. We have now 2 mocks for AGN based on 2 different extrapolation or prediction for the redshift population. One is based on the quite old Gill et al. 2007 cosmic X-ray background model, which is kind of pessimistic, and you can see it as a dashed line in this log n log s at redshift greater than 4, for example. And another one that is more optimistic is based on more updated Gill et al. 2014 luminosity function. The idea was to have a range of predictions, and the here the luminosity function is more or less in between these two. So we are covering the broad range. Both these mocks have a very wide rational luminosity range, and they go very faint in fluxes. That's important if you want to simulate deep pointings, also with other missions. We have galaxy mocks and cluster mocks. I don't have time to go into the details of all these. All the details are in this paper by Stefano Marchesi in 2020, and they are all publicly available at this website if you want to play with them. Other ingredients that you need to have a realistic simulation is diffuse galactic foreground. We have these 2 thermal components. Particle background, this is very simplified version of it, this red line. In magenta, you see the cosmic X-ray background, but you actually don't need it because it's already produced automatically by your catalog of AGN and galaxies, and then a dithering pattern for the survey. And what you get is these images of, for example, deep pointings on the left, shallow pointings on the right. And note there is no special clustering in these catalogs, so it's just random positions of all these different kind of sources. If we focus on one of these, this is a 1 megasecond pointings, so one of the deep pointings. Different colors for different energy bands. You see extended sources clusters, and then AGN with a variety of colors reflecting different spectral shapes, and so on and so forth. For the high redshift universe goals, we limit ourselves to the soft band, basically 0.722K band, to avoid strong foreground emission. And on these, you can run your preferred detection algorithm and derive from these your sensitivity of the survey. This is an example of run with wave detect, for example. We quickly realized that the final answer on the sensitivity of the survey strongly depends on the details of your detection tool, or detection algorithm. And so we started with wave detect that you probably know very well there at CFA. It's a great tool. It works basically out of the box, so it was very easy to implement. But then we realized that it was lacking the step of the PSF fitting, for example, and so position and fluxes were not very accurate, and we didn't have an handle on the likelihood of this detection. So with the help of Aitor Ibarra at ESAC, we developed, actually he adapted the XMM self-detection chain to 6P generated Athena-WFI data. Basically, it took a while, quite an effort, and now it's working great. And basically, this includes also the step of PSF fitting, and output catalogs now have you measure a detection likelihood both from the standard PSF fitting and defined as DetML. You may be familiar with that if you worked on XMM data. There is also Poissonian likelihood. It's more conservative and based only on number of source and background counts. This is for historical reasons, to compare with the old analytic estimates, basically. And we know that we have checked that there are accurate, we get accurate fluxes, position, and so on and so forth for the detected source. Of course, the key parameter in all this is having a PSF model. We have realistic PSF models and computed by Dick Willingale, and dependencies with energies and of axis angle, and these both go in the simulation and then in the analysis tool. So with this tool in hand, we can derive the realistic detection with the realistic sensitivity curves, given a detection threshold that you can choose. For example, in this plot, you can see two curves. One, the continuous one, is made for delta ML greater than 10. That is the standard for XMM beta. Of course, we will have to recalibrate this number for WFI because it will change. The fraction of spurious, for example, sources will change, and these need to be calibrated. And we had a student working on this. Here, I visited here last month. And the other one is for the more conservative cut based on Poissonian likelihood. Again, this is for historical reasons. We can ignore that for the moment. So the result tells you that for the 5 arcsecond PSF case, so the original proposal, also adding all the complexity of a realistic end-to-end simulation, we can meet the goals with the survey as it was designed. Also, this simulation can tells you that the degradation of the PSF has a major impact on deep, specifically on the deep survey, and therefore you will not be able to recover the same goal with the survey as it was designed for the 5 arcsecond. And most importantly, even if nominally the survey can get to very low fluxes, we can also show that there is a large fraction of confused sources in this range of fluxes highlighted in orange. And so, of course, it will be very difficult to derive a log n log S luminosity function at these fluxes. With the whole survey simulated, we can also derive the expected number of sources for both the two aims and in general for two redshift bin atoll luminosities. And you can see different columns that corresponds to different PSF values that we investigated in the last month and years, couple of years. The big boxes are for two different prescription of the luminosity function at high redshift, which makes a big difference. And in each box, you see two numbers again for two different likelihood cuts, one more conservative and one more standard, let's say. So you can see that there is a variety of predictions, and not only the PSF is affecting these results, but also clearly the input luminosity function that you use in your simulation. But this is kind of good. It's reflecting the fact that we don't know what's happening at those redshifts. Another thing that you can check and test with these tools is, for example, positional accuracy. That was a big we expected this to be a big problem when we started all this business, because, as I said, just from wave detect, the accuracy of the detection was not very high. And here you can see that this parameterized as the distance between the input source in the mock catalog and the position of the X-ray detection. And we can compute the fraction of sources for which this distance is less than 1 arcsecond. That is a number that was written in the original high redshift science goals for Athena and deemed to be relevant for high redshift sources because they are difficult to identify and so on and so forth. And you can see how this separation goes with flux and also detection likelihood, the threshold that you use, and again as a function of different PSFs. And again, the more conservative your detection likelihood, but the better the sources are characterized. So these are just a couple of examples of things that you can do with this end-to-end simulation. And once you develop an analysis tool that basically mimic what you will do in real life. Now, briefly on comparison with future mission and facilities. This is the actual yield of the WFI survey in black in a plane of bolometric luminosity versus redshift. Compared with 20 years of effort with Chandra and XMM in cyan, blue. I'm showing here only 3 surveys, 3 of the most famous, but they cover more or less all the parameter space that are covered by all the other surveys. So You will just have more numbers, but in the same range of luminosities and redshift. This is the situation if we add also the 20 years effort of optical near-infrared large area surveys. So SDSS, Euclid, Viking, PanSTARRS. And here on the bottom right, you can see how these numbers were collected in the past 20 years. These are mostly IND dropout selections. And in violet, you can see new results from shell Q. So basically, the Subaru Viper Spring camera, they by going deeper on a 600 square degree area, they managed to go almost 100 order of magnitude deeper in luminosities. But all these sources are by selection broadline AGN, type 1 AGN. We started seeing a few narrow line candidates in shell Q, and there are 3 sources that I know of that are X-ray obscured when you follow up them with X-rays. One is this one that we published this year. It's highly obscured, but it's a lens quasar, so that these, of course, help in collecting a decent spectrum. And there are other 2 candidates, competency candidates on the base of HART-only detection. So these are less secure. So why this is relevant? Well, the same will be true also for the Euclid selected. Here I'm showing predictions from the high redshift quasar detected by Euclid, and the same will be true also for the combination of Roman and Rubin selected candidates. I don't have actual simulations, but the range that they claim they will cover is extending the range in redshift up to 10 and going deeper in luminosities. But again, this will all be by selection, narrow line, and type 1 AGN. Why this matters? Because we know that obscuration at high redshift is relevant. We have observed this in the last years. We know that the fraction of obscured sources increase with redshift, or the average column density increases. These are a couple of examples of results from Chandra big surveys. We think that this may be related to the ISM becoming denser and denser at high redshift. And I think Roberto Gilli gave a talk to this same audience a couple of weeks ago on this paper that we published this year on a simple model trying to reproduce the observed trend in average column density and obscured fraction in terms of the contribution of the ISM that becomes denser and denser at high redshift, plus the steady contribution from the torus. And we see also in simulation, these are a couple of examples of sources, AGN surrounded by large columns of gas and dust at high redshift. As a consequence of all this, we expect that more than 90% of high redshift AGN may be missed by UV selection techniques due to obscuration, and this is basically no matter what the sensitivity. You can possibly detect the host, but you will not detect the AGN. And this fits quite well also with this comparison between the redshift 6 QSO luminosity function in the UV and the extrapolation of what we know at lower redshift in the X-rays. There is 2 orders of magnitude mismatch between these 2. So there is a huge discovery space for Athena-WFI, or in general X-ray surveys in the 30s. There is actually one tool that is competing for obscured AGN, and these are deep radio surveys. These are a couple of plots from an exercise that we did for SKA a while ago. You can see here volumetric luminosity again of the AGN and the area covered by the different surveys, and basically Athena-WFI, SKA, and WFIRST are the only ones collecting large number of sources in the Compton-Thin regime, even if WFIRST again will detect the hosts and not much the AGN. But if you look at Compton-Thick AGN at redshift greater than 6, SKA the pointings will work even better than X-rays because they are not affected by the large obscuration. Of course, there is a big problem here. As they stated in this SKA paper by Afonso 2014, the biggest challenge will be to identify such sources among the millions that will be detected. And here the authors say that the combination with optical near-infrared surveys will be necessary. But for what I have shown, I think in reality, the combination will be mandatory with X-ray surveys, either Athena-WFI or some other X-ray survey. But it's what really you need to detect these obscured sources. And with this, I come to my conclusions. So I've very briefly shown you some of the results of our end-to-end simulation on the Athena-WFI survey, and in particular, the fact that we confirm that we can detect tens to hundreds of AGN, and this strongly depends on the PSF. So there was a huge effort in trying to get the PSF as close as possible to the original proposal. And very interestingly, to the assumed luminosity function, which at the moment spans a wide range of values. And I think in the 30s, Athena-WFI will be competitive with respect to other planned facilities and surveys, especially because of this problem of obscuration, that high ratio is going to be very important. And so will be complementary to optical near-infrared surveys and also needed to identify highly obscured AGN in deep radio surveys. And I will stop here.
Thank you, Giorgio. Any questions from our in-person attendee at first? Please.
Hi, Giorgio. This is Thomas Connor.
Hi.
So I really liked the slide you had showing how most of the shell cues and Viking and everything and all of those quasars are much more luminous than what we're hoping to see with Athena. But since 2010, we've obviously drastically increased the number of high luminosity. Yeah, that one. We've drastically increased the number of high luminosity quasars that we know in this epoch. And so I'm wondering if since 2010, if there's been any change in the survey strategy in order to minimize just how much we care about the high luminosity ones and focus solely on going for the most faint possible targets.
Well, the design of the original survey was already pointing to let's go deeper in luminosities, because of course we knew that a large number of sources will be discovered with wide area optical near-infrared surveys. The specific design of the survey have changed quite a lot in the study during the study phase to accommodate for changes in the expected mission lifetime, for example, that was reduced due to costs and things like that. And one of the goals of this end-to-end simulation business was to be flexible enough to adjust the survey strategy to any kind of new input that we could make. We were limited to for example, going deeper instead of going wider in order to avoid replicating the same sources that would be already discovered by the 30s, by the PSF, basically. You cannot go much deeper. And so it was a trade-off between we don't want to waste time going very deep if we don't have the PSF to do that. But at the same time, we don't want to go very wide because it would be a already covered parameter space.
Thanks.
But this will change probably again.
Yeah. Any questions from our? Yeah, please.
So I think you've left off the survey type that's going to win, which is millimeter wave surveys. The South Pole Telescope 3G survey discovers one object at Z greater than 7, and there's really no problem with distinguishing it from lower redshift objects, and it can be quickly checked with ALMA. So the amount of integration time is on each source to discover it is really very minimal. So there will be thousands of such high redshift objects.
You're right. That's my fault, and I for sure will add this to the slide. And what's the kind of sky coverage that this will reach, if I may? that will be the thing to address.
Martin, I saw you raise your hand, please.
Hi, Giorgio.
Hi, Martin.
Uh,
Nice to meet you.
whoop. So I wanted to make a comment on overlapping with the optical surveys in that it's not just finding these objects. We want to study the UV X-ray ratio for cosmology reasons, and as well as understanding black holes. So there's a good reason to do that. But maybe that means adjusting the strategy. But I did just want to confirm that the PSF model you're using is the current one with the half power diameters of what, 8, 10 arc seconds?
We have a variety of half power diameter values. So we keep doing these simulations and testing with 5. That is always the goal. And then there was a huge study between 7 and 8 because it looked at that was the number that was going to be in the end. Then at some point there was a warning, and we added the 10 arc second value. That the problem is that we don't know. The latest calibrations were pointing towards, again, back to something between 7 and 8. So we keep all this version of the survey together because they have the most probable value have changed a lot in the last few years. That's the problem.
But for the plots you showed, what were you using?
For this plot is the 5 arc second.
5. Okay.
Yes,
That's a little optimistic.
This was optimistic, but of course, things
Okay.
with 10 are much worse. 7, 8, not that terrible. But the good thing is that these are not more Gaussian. We have proper ray tracing and simulation of what's the real shape of the PSF, and these turned out to help a lot because the typical PSF is as a narrow peak and then wide tails, and this helps a bit in recovering the power detection and identification power.
Okay.
That doesn't scale linearly with the value of power diameter, which is only approximate the global shape of the PSF.
Yeah, that's good news. So the full width max is smaller with the
exactly. Typically, the full width al maximum is smaller, and it evolves more slowly than the corresponding half power diameter. So the core is staying more stable, and then you have broader wings. But the net effect is that it's a bit better than what you expect for the Gaussian.
That's good news. Thanks.
Do we have any questions from in person or online? Okay, if no, let's thank both speakers again. Thank you very much for coming.
Thank
See you
you.
next week.
Thank you. Bye.
Thank you, Giorgio.